Before starting with this chapter on the center of mass, let us just get a brief idea of where center of mass or the center of gravity would have originated from. Now, center of gravity is a more intuitive term, is a more intuitive thing than the center of mass. There is a subtle difference between these two. Center of gravity may not always exactly coincide with the center of mass, but barring that special case where they are not one and the same, in most of the cases the center of gravity and the center of mass is one and the same. So let's start with what a center of gravity is, and then extend that idea to what a center of mass is. Now suppose you have got a large object, and until now we have dealt with objects that are small in size, and we say that the objects are like particles. But now from this chapter onwards we are going to deal with large objects. So suppose we have got a large object somewhere like this, arbitrarily shaped, and this object for the time being we will think of it as a two-dimensional object. So it's like a plate, and this plate has got some area, some size, and so it has got some mass, it has got some weight. Let us say that its mass is m, so its weight is mg, and this weight or the gravitational force that is acting on this object tries to pull this object downward towards the earth, and this force should in effect be acting at all small segments of this body. So this huge object which I have here, I can break it up into small pieces, and I can say that there is a small downward force on each of those pieces, and if I add up all those small downward forces, I will end up having this large downward force mg. So I can say that the weight of this object is really distributed throughout its volume or throughout the surface area if I'm thinking of a two-dimensional object. So a small weight acts through every point, and so in order to balance this object, a distributed upward force is needed to keep the object in equilibrium. Now what I mean is this: let's say I think of this object and I break it up into small pieces, one blue piece here, another blue piece there, and some other blue piece somewhere here, and another blue piece somewhere over there, and at each of these blue pieces there is going to be some weight acting in the downward direction. So delta m1 into g, I've got delta m2 into g, I've got delta m3 into g, I've got delta m4 into g, and so on, and I can do this for all the infinite small chunks of which this object is made up of. Now if I have to balance this one piece whose weight is delta m1 into g, probably I need to apply an upward force at that piece, and that should be equal to delta m1 into g. That should be the amount of upward force exerted on that specific piece to keep that piece in equilibrium. Now to keep this piece in equilibrium, I should apply an upward force of delta m3 into g. To keep this piece in equilibrium, I should apply a force of delta m2 into g, all in the upward direction. So the idea is that in order to keep this object in equilibrium, my expectation is that the upward force should also be distributed throughout the surface of this object. Or my expectation is that because of the distributed nature of weight, a distributed upward force is needed to keep this object in equilibrium. Now when I work with this object practically, and you can easily think of an example, maybe not of a two-dimensional object, but you can think of the example of maybe a one-dimensional object, a rod. If you work with a rod, which also happens to be a distributed weight kind of an object, you see that you will be able to balance the rod by applying not a distributed upward force but a concentrated upward force at exactly one point. So we observe that it is possible to balance this object or to keep it in equilibrium, keep it in vertical equilibrium, by applying a single force which is equal to the total weight at an appropriate point. And then we started thinking that if it is feasible to keep this object in vertical equilibrium by applying this force in the upward direction at an appropriate point, then will it not be reasonable to assume that the total weight of this object acts in the downward direction through that point. So this implies that, and this led us to the understanding that the total weight of the object acts in the downward direction through that point. And then we started naming this point as the center of gravity, because it appeared as if that entire gravitational force was centered at this particular point. This point was called the center of gravity, and that later on gave rise to the idea of center of mass. Now, people, we have to keep in mind that this idea is not always true. So if you have an object and you want to keep that object in vertical equilibrium by applying an appropriate force that is equal to its weight at an appropriate point, that's not always feasible. We have found out afterwards that the center of gravity of an object may lie physically outside the body. So you can have an object like a ring, and the center of gravity does not lie within the ring anywhere. And by saying within the ring, I mean to say that it doesn't lie anywhere in the material of the ring. It lies at the center of the ring, which is a point where there is no material. So physically it will be impossible to apply a force at the center of the ring and still keep the ring in vertical equilibrium. So this idea is not foolproof. This is only a preliminary analysis. We understood this because we were dealing with rods, we were dealing with plates, and we found out that for a rod or for a plate such a point exists. And that point was then called the center of gravity, and that gave it gave rise to the idea of the center of mass. But of course, afterwards, when we started analyzing these ideas in a bit more detail, a bit more formally, a lot of things emerged out. So these days we have got a very formal understanding of what the center of mass is, what the center of gravity is, and we are not going by our intuition anymore. And my aim will be to formally introduce the idea of center of mass to you people, but before formally introducing it, maybe a few examples. So first, for this entire chapter, we will assume that the center of mass and center of gravity are one and the same. So there is a subtle difference between them, and that difference will come in when the object is very large, such that the gravitational force at different points, or not the force, the gravitational field at different locations on the object itself varies. So maybe you're talking about something as tall as maybe Mount Everest, or maybe even taller. And then the amount of gravitational field at the base of this object and the amount of gravitational field at the top of this object are going to be different, and that is when the center of gravity will be different from the center of mass. But the objects that we are going to deal with in this particular chapter, you will have the center of gravity and the center of mass as one and the same. So keep in mind that if you have something really tall like Mount Everest, where the value of G is high at the base and the value of G is low at the top, then you will have the center of gravity somewhere towards the base of this object, but the center of mass may be somewhere else, and this object has to be sufficiently tall enough. But then our everyday objects are not of this kind. Our everyday objects are very small sized objects. Even if you think of a building which is maybe around 1000 meters tall, the difference between center of gravity and center of mass is negligible. So for the purposes of this particular chapter, we are going to assume that center of mass and center of gravity are one and the same. That's number one. Number two, we will work with some intuitive ideas that we have, and those intuitive ideas, they say that if you have a uniform object, then the center of gravity will lie on an axis of symmetry. So say for example you have got a uniform rod. You have got a uniform rod like this. The center of mass or the center of gravity will lie at the geometric center of this rod. Center of mass. This is a uniform rod here. You may also have a uniform circular disc. So if you have got a disc-like shape like this, then the center of mass will be again at the geometric center, this point here. This is the center of mass. This is also the center of gravity. If you have got a uniform rectangular plate, if you have got a plate like this, Then again, the center of mass of this entire plate will be a point at the geometric center, which will also be the point of intersection of the diagonals, as long as this is a uniform rectangular plate. If you have got a uniform sphere, if you have got a uniform spherical ball or a uniform sphere, the center of mass will be at its geometric center, which will be present inside the ball or the sphere, and we will not be able to really apply a force at that particular point, but we will be able to apply a force at a point which is directly beneath that point on the surface to keep the ball in equilibrium. So please keep in mind that center of mass or center of gravity of an object may lie outside the material of the object, and examples of this kind will include uniform rings whose center of mass is their geometric center but it lies outside the material of the ring, or maybe a uniform spherical shell whose center of mass is again the geometric center which is outside the material of the shell itself. Of course, in both cases, in case of a uniform ring as well as the uniform spherical shell, the center of mass lies within the area occupied by the ring or within the volume occupied by the spherical shell, but it is not within the material, right? So keep in mind that these are all very intuitive ideas. The things that we have been discussing are very intuitive ideas. If there is a uniform object, the center of mass will lie on an axis of symmetry. That means if the object has two axes of symmetries, two or more, then they will be concurrent, and the point of their intersection will be the center of mass. But I guess a proper way to study center of mass and to go ahead with this chapter is to actually define it formally. So that is what I'm going to do next, people. Let us go towards a formal definition of center of mass.